Alright, let's go. Number 10. The double-slit experiment that watches back. In 1801, English polymath Thomas Young performed an experiment that should have been simple. He shone light through two narrow slits and observed the pattern it created on a screen behind them. Instead of two clean bands of light, he saw an interference pattern, alternating bright and dark stripes that proved light behaved as a wave. For over a century, this was considered settled science. Then in the 20th century, physicists repeated the experiment with individual particles, and reality began to unravel. When electrons are fired one at a time through two slits, they still create an interference pattern, as if each electron somehow passes through both slits simultaneously and interferes with itself. This alone was strange enough to disturb the foundations of classical physics. But the truly disturbing discovery came next. When researchers placed detectors at the slits to observe which path each electron actually took, the interference pattern vanished. The electrons began behaving like ordinary particles, passing through one slit or the other. The act of observation changed the outcome, not through physical interference, not through any measurable disturbance, but through observation itself. The particles seemed to know they were being watched. What makes this experiment particularly disturbing is what it suggests about reality's foundation. Matter does not appear to exist in a definite state until something observes it. Before measurement, particles exist as probability waves smeared across all possible locations simultaneously. Only the act of observation collapses these possibilities into a single definite outcome. Physicist John Wheeler called this a participatory universe, one that requires observation to become real. If your kitchen table only exists in a definite state because consciousness is measuring it, what happens in the rooms you are not looking at? The universe might be rendering itself on demand, calculating only what needs to be observed, leaving everything else as mathematical potential. Number 9. The fine-tuning of physical constants. The universe operates on roughly 30 fundamental constants, numerical values that determine how reality functions. The strength of gravity, the mass of the electron, the cosmological constant, the ratio of electromagnetic force to nuclear force. These numbers are not derived from any deeper principle. They simply are what they are, and they are calibrated with impossible precision. Physicist Paul Davies calculated that if the cosmological constant differed by 1 part in 10 to the 120th power, the universe would have either collapsed into a singularity within moments of the Big Bang, or expanded so rapidly that no atoms could form. If the strong nuclear force were 2% stronger, no hydrogen would exist. If it were 2% weaker, no elements heavier than hydrogen could form. If gravity were slightly more powerful, stars would burn through their fuel in mere millions of years, far too fast for life to develop on any orbiting world. Every constant sits within an incomprehensibly narrow window where atoms, stars, planets, chemistry, and eventually consciousness become possible. Change any one value by a fraction of a percent, and the universe becomes sterile or never forms at all. The mainstream scientific response to this is the multiverse hypothesis. Perhaps infinite universes exist with every possible combination of constants, and we inevitably find ourselves in one of the rare configurations that permits observers. But this explanation requires believing in an unobservable infinity of realities to explain the one we can see. There is another interpretation that many find even more unsettling. The constants are not tuned by accident or by statistical inevitability across infinite cosmoses. They are tuned because someone or something tuned them. The universe has the appearance of a system with parameters set by an operator. The precision looks less like physics and more like configuration. You are living inside a framework where the dials were turned to specific settings before the program began executing. Number 8. The Planck limit and pixelated spacetime. In 1899, physicist Max Planck derived a unit of length from 3 fundamental constants. The Planck length measures approximately 1.6 times 10 to the negative 35th meters. At distances smaller than this, the known laws of physics break down completely. Space itself appears to have no meaning below this scale. Time has a similar limit, the Planck time, roughly 5.4 times 10 to the negative 44th seconds. Below these thresholds, the universe refuses to be measured. For decades, physicists assumed the Planck limits were simply the boundary of our current understanding. More advanced physics would eventually describe what happens at smaller scales. But an alternative interpretation has gained serious traction among theorists. The Planck length is not a limit of measurement. It is the resolution of reality itself. Think about what this means. A digital image appears continuous at normal viewing distance, but zoom in far enough, and you discover pixels, discrete units that cannot be subdivided. The image was never truly continuous. It was always a grid of individual points. Some physicists now argue that space and time work identically. You cannot measure below the Planck scale because there is nothing below it to measure. Reality is pixelated. Physicist John Wheeler, along with researchers at Fermilab, has spent years searching for evidence of this pixelation through experiments designed to detect quantum jitter at the Planck scale. If spacetime is discrete, it should exhibit small, measurable fluctuations as objects move across its grid. The preliminary results have been ambiguous, neither confirming nor ruling out the hypothesis. What makes this particularly unsettling is the computational implication. Digital simulations always have a minimum resolution, a smallest unit below which the simulation does not bother to calculate. The Planck scale looks suspiciously like that boundary. If you were running a simulated universe on finite hardware, you would establish exactly this kind of lower limit to conserve processing power. The cosmos appears to have a pixel size, and the pixel size is precisely where we would expect it to be if reality is running on a system with computational constraints. Number 7. The delayed choice, quantum eraser. In 1999, physicist Yoon-Ho Kim and his team performed an experiment that attacked causality itself. They built a more sophisticated version of the double-slit experiment with a critical modification. The decision to observe or not observe which path a photon took could be made after the photon had already hit the detection screen. The result defied every intuition about how time works. When the path information was recorded, even after the photon had apparently completed its journey, the interference pattern disappeared. When the path information was erased after the fact, the interference pattern appeared. The past behavior of the photon seemed to change based on decisions made in the present. The photon did not travel through the experiment and then get measured. The photon's behavior in the past was determined by measurements made in its future. Cause and effect. The fundamental structure on which all of physics was built appeared to run backwards under specific conditions. Physicists have proposed various interpretations to explain this without violating causality. Some argue the photon exists in a superposition of histories until measurement selects one. Others suggest information travels backwards through time in limited ways. None of the explanations are comforting. All of them require abandoning the idea that the past is fixed and the future is undetermined. The simulation interpretation handles this elegantly. In a computed reality, the past does not exist as a completed record. It exists as calculations that only resolve when observation requires them to resolve. The system does not bother determining what actually happened until something asks the question. When you think about a memory, the universe may be computing that memory on demand, generating a coherent past that did not exist in definite form until you needed it to. The continuity of your life from childhood to this moment may be a render job, assembled retroactively each time consciousness requires a history to make sense of the present. Number 6. Mathematical elegance where it should not exist. In 1960, physicist Eugene Wigner published an essay titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He pointed out something that should disturb anyone who stops to consider it. Mathematics, a system humans invented to count sheep and measure fields, describes the deepest structures of reality with impossible accuracy. Consider that abstract mathematical concepts developed for pure intellectual curiosity with no connection to the physical world repeatedly turn out to describe fundamental physics decades or centuries later. Non-Euclidean geometry was developed in the 19th century as a mathematical curiosity. Einstein used it to describe the curvature of spacetime. Complex numbers involving the square root of -1 seemed like pure abstraction. They turned out to be essential for quantum mechanics. Group theory was invented to solve equations. It now describes the fundamental symmetries that govern particle physics. The universe does not merely permit mathematical description. It appears to be made of mathematics. Physicist Max Tegmark proposed the mathematical universe hypothesis, suggesting that physical reality is not just described by mathematical structures, but literally is a mathematical structure. Every particle, every force, every moment of time is an expression of mathematical relationships. This should give you pause. Why would physical reality, if it arose from natural processes, conform so precisely to abstract mathematical patterns that humans can derive without looking at the universe at all? A thrown rock does not need to solve differential equations to fall, yet differential equations describe its fall perfectly. The universe behaves as though it is running on mathematics, not merely being described by mathematics. If reality is fundamentally computational, this is exactly what you would expect. Simulations run on code, and code is executed mathematics. The strange beauty and predictive power of mathematical physics might not be revealing the deep truth of nature. It might be revealing the source code of the environment you inhabit. Number 5. The holographic principle. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed something that sounds like pure science fiction. They argued that all the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary. The interior is not truly three-dimensional. It is a projection. The idea emerged from studying black holes. Physicist Jacob Bekenstein had calculated that the information content of a black hole is proportional not to its volume, as intuition would suggest, but to its surface area. This seemed impossible at first. How could the information describing everything inside a black hole be stored on its outer surface? Yet the mathematics were unambiguous. Extending this principle further, T. Hooft and Susskind argued that the entire universe might work this way. What you perceive as three-dimensional reality could be a holographic projection from information encoded on a distant two-dimensional surface. In 2017, researchers at the University of Southampton, working with scientists in Canada and Italy, published findings that appeared to provide observational support for the holographic universe model. They found that certain patterns in the cosmic microwave background, the afterglow of the Big Bang, matched predictions from holographic theory as well as or better than the standard cosmological model. What makes this particularly disturbing is what it implies about the nature of what you experience. The depth you see when you look across a room, the three-dimensional solidity of the chair in front of you, the volume of space your body occupies. All of these may be illusions generated by information stored somewhere else entirely. Your sense of inhabiting a three-dimensional world might be as real as a character in a video game sensing the space inside a rendered environment. You are not in the universe. You are on its surface, projected inward, experiencing depth that does not fundamentally exist. The room around you might be painted on a cosmic wall you cannot see, and your perception of three-dimensional reality might be the most convincing illusion the mathematics of physics can generate. Number 4. Quantum entanglement and information beyond space. In 1935, Albert Einstein collaborated with physicists Boris Podolsky and Nathan Rosen to publish what they believed was a devastating critique of quantum mechanics. They described a scenario where two particles could become correlated in such a way that measuring one would instantaneously determine the state of the other, regardless of the distance between them. Einstein dismissed this as spooky action at a distance. He was certain the effect could not be real because it would require information to travel faster than light, violating his own theory of relativity. Einstein was wrong. Quantum entanglement is real. Beginning with physicist John Bell's theoretical work in 1964 and confirmed by increasingly sophisticated experiments through the 1980s, 1990s, and 2000s, entanglement has been verified repeatedly. Two particles can be entangled such that measuring the spin of one instantly determines the spin of the other. The effect has been demonstrated across distances of over 1,200 kilometers in experiments involving satellite-based quantum communication. The information transfer appears to be instantaneous, regardless of separation. For decades, physicists insisted this could not be used to transmit usable information faster than light, and therefore did not technically violate relativity. But the correlation itself is undeniable. Something is happening that ignores the space between the particles entirely. They behave as though the distance is irrelevant, as though they are, in some deep sense, the same object regardless of where in the universe they are located. The simulation interpretation of this is almost too clean. In a computed reality, two objects that share common information do not need to be physically connected. They are just shared variables in the same program. When one variable is updated, the other updates instantly, because there is no actual distance between them inside the code. The appearance of separation is a feature of the rendered environment, not the underlying computation. Space itself might be a convenient fiction the simulation presents to observers, while the real structure connecting objects has nothing to do with distance at all. You perceive stars as being trillions of kilometers away. The underlying reality might not include distance in any meaningful sense. You are moving through a dimensional illusion. An entanglement is the occasional moment when the illusion fails to hide its underlying architecture. Number 3. Cosmic microwave background anomalies. In 1964, radio astronomers Arno Penzias and Robert Wilson accidentally discovered the afterglow of the Big Bang itself. The cosmic microwave background is a near-uniform field of microwave radiation permeating the entire universe, a photograph of the cosmos as it existed 380,000 years after its beginning. For decades, scientists treated it as the ultimate smooth backdrop, the canvas on which the story of cosmic evolution unfolded. Then we looked closer. In 2013, the European Space Agency's Planck satellite produced the most detailed map of the cosmic microwave background ever made. The data revealed anomalies that should not exist according to standard cosmology. The universe showed a large cold spot in the southern hemisphere, an unexplained region of below-average temperature spanning billions of light-years. There was an alignment of large-scale structures with the plane of our solar system, a pattern researchers nicknamed the axis of evil, because there is no reason cosmic-scale structures should align with our tiny local perspective. The probability of these alignments occurring by chance is vanishingly small. Some cosmologists have spent years searching for statistical explanations. Others have proposed more unsettling interpretations. The universe appears to have preferred directions, despite theory requiring it to be isotropic. It appears to have structures that correlate with the position of Earth, despite Earth having no cosmological significance. One interpretation gaining quiet support in certain theoretical circles is that these anomalies are computational artifacts. In any simulation, rendering the entire universe at full resolution would be prohibitively expensive. A computationally efficient simulation would render high-resolution detail only near the observer and use lower-resolution approximations for distant regions. The boundaries between resolution zones would create exactly the kind of patterns we see: alignments with the observer's position, unexpected cold spots, irregularities that correlate with perspective rather than cosmology. You may be looking at evidence of the rendering engine. The universe might have shortcuts baked into its largest structures, and we are only now developing instruments sensitive enough to detect them. Number 2. Consciousness and the measurement problem. For nearly a century, physicists have tried to explain what happens during quantum measurement without appealing to consciousness. The explanations have grown increasingly desperate. Every proposed mechanism for wave function, collapse, decoherence, spontaneous localization, the many worlds interpretation has failed to fully explain why observation produces the specific effects it produces. In 1932, mathematician John von Neumann proved something that still haunts physics. He demonstrated that the measurement chain in quantum mechanics cannot be closed without introducing something non-physical. A measuring device is made of atoms governed by quantum mechanics. The atoms require measurement to collapse into definite states. The measuring device itself is therefore in a superposition until observed by another device, which is also in superposition, continuing indefinitely. The chain only terminates when it reaches consciousness. Something non-mechanical has to break the recursion. Physicist Eugene Wigner extended this argument. He proposed that consciousness is not merely a product of physical processes, but plays an active role in determining physical outcomes. For decades, this was considered fringe thinking. Most physicists assumed a purely mechanical solution would eventually be found. None has been found. The measurement problem remains unsolved. Philosopher David Chalmers has separately identified what he calls the hard problem of consciousness. Physical processes in the brain can, in principle, explain behavior and information processing. They cannot explain why there is subjective experience at all, why there is something it is like to be you, looking out through your eyes, rather than mere unconscious information, processing producing identical behavior without any inner experience. These two problems, the quantum measurement problem and the hard problem of consciousness, may not be separate problems at all. They may be the same problem viewed from different angles. Consciousness is the thing physics cannot explain. The element reality cannot be reduced to, the factor that collapses probability into outcome. In a simulated universe, this makes perfect sense. The consciousness experiencing the simulation is not part of the simulation. It is the user, the observer on the outside, the thing for whom the simulation exists. You are not a character in the program. You are the player, and the program needs your attention to know what to render into existence. Number 1, the mathematical structure of everything, and the closing of the frame. Physicist John Wheeler spent the final decades of his life pursuing a single idea. He called it from bit. He argued that the universe, at its deepest level, is not made of matter or energy. It is made of information. Every particle, every force, every event in the cosmos is fundamentally a bit. A yes or no answer to a question, a piece of data being processed by some underlying system. Wheeler was not alone. Physicist Seth Lloyd at MIT calculated the computational capacity of the universe itself. He estimated that the observable cosmos has performed approximately 10 to the 120th logical operations since the Big Bang, operating on around 10 to the 90th bits of information. In his 2006 book, Lloyd argued that the universe is literally a quantum computer, computing its own evolution. Every particle interaction is a computation. Every moment of time is a processing cycle. Physicist James Gates, while working on string theory equations, discovered something in 2010 that disturbed him enough to speak about it publicly for years afterward. Embedded in the mathematics describing the fundamental nature of matter, he found error-correcting codes. Specifically, he found a type of code called a doubly even self-dual linear binary, error-correcting block code. These are the exact types of codes used in modern computer systems to ensure data integrity when information is transmitted across unreliable channels. They are a product of computer science, not physics. Yet they appear in the equations that describe reality at its most fundamental level. Gates was clear about how this made him feel. He stated publicly that the presence of these codes in the equations of physics suggested we might be living in something resembling the Matrix. This was not a philosopher speculating. This was a physicist reporting what he found in his equations. Consider the weight of everything we have examined. Particles that only become definite when observed. Physical constants tuned to impossible precision. A minimum resolution of spacetime at the Planck scale. causality that runs backwards under specific experimental conditions, mathematics that describes reality with unreasonable accuracy, a holographic principle suggesting three-dimensional space is a projection, entanglement that ignores distance entirely, cosmic anomalies that correlate with observer position, consciousness that cannot be reduced to physical processes and that reality itself seems to require, error-correcting codes embedded in the fundamental equations of physics. Any one of these findings might be explained away. Each has alternative interpretations within conventional physics, but taken together, they form a pattern. They all point in the same direction. They all suggest that what you perceive as physical reality behaves exactly as a sufficiently advanced simulation would behave, exactly as a computed environment would behave, exactly as a rendered framework calibrated for observers would behave. You have spent your entire life believing in the solidity of the world around you. You believe the stars are real, that the ground beneath you is material, that the distance between objects is genuine, that your memories record events that actually occurred, that your consciousness is a product of the physical brain inside your skull. Every one of these beliefs is now in serious scientific question, not because a philosopher argued against them, but because physics itself, pursued to its deepest level, keeps returning evidence that reality is not what it appears to be. The universe looks less like a natural phenomenon and more like an output. It looks less like a thing that exists and more like a thing that runs. You are not discovering how the cosmos works. You may be discovering that the cosmos is a construct, and that the question you should be asking is not what the universe is made of, but who or what is running the calculation you currently inhabit. If you want to see more videos like this, click the video on screen now and make sure to subscribe.